Hi everyone, welcome to Byte Ventures, where we deep dive into the marvels of technology. In today's case study, we'll discuss about how Twitter manages its hyperscale read requests into its users' database. Without further ado, let's dive deep in. So Twitter receives a huge amount of read requests into its user database because Twitter operates on one of the world's largest user reservation system, or otherwise known as URS. The URS is currently managed by something called as Gizzard. So Gizzard is an in-house sharding framework built by Twitter during 2010. Don't worry. If you don't know about Gizzard, we'll discuss in depth in a short. Let's see, why do they have a system called Gizzard, and what exactly was it serving? What were the architectures behind it? And why there was a need to revamp this old architecture into something that is present in the current day. So after 2000s, a lot of modern websites required large amount of information to be stored and shared across. So it was really infeasible to store such kind of huge information in a single computer. And that is when Google came up with something called as sharding. So Google termed or coined sharding, and it got popular in its big table research paper that got published in 2006. So if you talk about sharding in layman terminologies, sharding consisting of two terms. One is partitioning, one is replication. So partitioning. So the basic premise that sharding came into existence because a single computer was not enough to store all of the data, right? So that means we need to partition the whole bigger data frame into smaller chunks so that each smaller chunk can reside in a computer pretty efficiently. Replication. So now that when we have divided a bigger part into smaller chunks, we don't want any of the smaller parts to get messed in case of any disasters, right? In case of any failures. That is why we need to have proper replication strategy in place to store the whole data in one piece. But sharding is inherently difficult because of the use of smart partitioning schemes. A developer has to put a lot of thought onto how and why to partition it so that the queries are efficient, they don't waste a lot of space, and they serve the right purpose for which it was broken down into pieces. Now that we have different copies, it is very important yet difficult to manage consistency across all of the copies. So in other words, Gizzard is a middleware networking service which was sitting in between the client app and the database replicas. So it abstracts out all the complexities for managing shards, routing the queries to the respective shard as per the request, and it handles the replication in case of any such failures. This looks like an effective solution, right? Then why is Twitter moving away from Gizzard? Very important thing. So first, it was getting very challenging for them to maintain the strict service level objectives on the query per second that they're receiving. They were receiving almost millions of query per second in current terms because of the high or the heavy influx of the users into the platform. They were not able to control the latency that they wanted to have in the first place. And that was a huge concern in getting rid of the Gizzard framework. Maintaining consistency across different data centers was a huge challenge that was posed because their service was built around 2010, and over the years the request was a completely different architecture. It required a lot of different processes to come into the place. Meanwhile, they have to do all of this while churning out new features on the existing platform. This took a huge hit because they're not able to manage the developer productivity because of the huge downtimes that they were facing. And that was the primary concern in thinking about an alternative of Gizzard. Okay, so what exactly is the solution in this case? So after a lot of brainstorming and a lot of use case analysis, they finally figured out that Vitess is a solution. So what exactly is Vitess? So Vitess is an open source database clustering system for horizontal scaling of MySQL databases. So as Twitter's most of the business was their on-prem MySQL clusters, they thought that this would be an excellent fit for the problems that they were facing. Vitess was very instrumental in addressing the challenges associated with scaling traditional relational databases. It was made by Google. It was made by YouTube actually, and it was open sourced by Google later. Its performance, its reliability, the community, and the ease of use made it very popular for Twitter to think about that this is a very viable solution for the problem that they were facing. Okay, let's think about how Vitess was born. So let's think about the journey that every small company faces, right? So when there is a small company, there is a simple database that receives all of the read requests and that receives all of the write requests, right? Because the traffic is not huge and a single database can manage things pretty effectively. Now, when things scale, when there is more read request, we would need something of this structure wherein we have a master and we have a replica, or a leader follower architecture, a master slave architecture, whatever it's called, where the write is routed to the master database and all of the reads are routed to the replicas, and the replicas in certain time intervals, which is configured, syncs itself to master and gets the latest data so that there is consistency. In this case, there is a lot of terminologies around what if master dies when there is a sync and all stuff, which is not scope of this video. We'll cover that in a later video, how things work in case of any failures, how the eventual consistent state is reached and stuff like that. So for now, let's assume that everything is working perfectly. The write are getting routed to the master database. The read are queried into the replicas. Replicas are syncing properly. And in case of any failures, one of the replicas gets the master database or gets in charge of the master database. Okay, things are pretty interesting, right? So now that the reads can be handled, we can add multiple replicas in this case so that this would eventually handle the read traffic. But what if we have more number of write requests coming in? This will be bottleneck, right? Because there is a single master database, the write will have to manage somehow this bottleneck so that we achieve the kind of performance we kind of expect out of this system. That is when we build a system where we have multiple master databases in place, right? So now that we have multiple masters, we have multiple replicas. But now that we have implemented sharding for the write queries, it's very important for us to handle the failures and disasters if that happens. That is very important. And that is why it's very important for us to understand and implement replication. That is why this is the whole architecture that becomes. So whenever there is a huge kind of writes, we shard it, and to handle the faults, handle it in case of any failures, we add a bunch of replication, which in case of any such downtime, will make sure that they're available, right? But what do you think of this? Like, instead of solving a huge problem, we introduced many more smaller problems. Like, think about the maintainability. Think about the management of this whole service. How do you know then when one of the service or one of the database goes down? What if the master database goes down, and which of this needs to be upgraded to the master? There's a lot more different problems that got introduced because of the huge system. So what if this whole thing could serve as a single database with enough abstraction, right? That would make our life much more simpler. And that's exactly what Vitess did. So Vitess encapsulated all of this as a single black box. So this is the black box that it provided itself, provided to the outside world, and told that, okay, now you can use this structure as an independent, highly horizontally scalable SQL database, right? Okay, let's see how this works internally. Okay, let's talk about the Vitess components that we have. So there are certain critical components for which Vitess is very, very popular. And one of them is the VT tablet. So the VT tablet is the one which is residing on top of the MySQL server. So VT tablet is the proxy to the MySQL server. And whenever there is a query that comes in, it reaches the VT tablet. So this is the VT tablet and this is the MySQL server. And it routes the traffic to the MySQL server and performs the respective tasks that were required for this request. The next thing that is very important And as an important part of components is the topology cloud. So the topology cloud is like a configuration source where all of the configuration, all of the logs are kind of stored. It keeps track of all the connected VT tablet, the master failovers, any kind of recycling needed to any of the servers, and handling all kinds of faults are the responsibility of this topology cloud. The Vitess, as part of YouTube, implemented this part using Chubby internally, and they used Zookeeper as something which they open sourced it. VT-Gate. So VT-Gate is a critical component. It's like a gateway for the external apps. The external app would connect to the VT-Gate, and the VT-Gate would internally migrate those requests to the corresponding VT tablet as per the need basis. It would identify the correct shard, and then it would route the traffic to the correct shard, and eventually those shard will reach the MySQL server and we'll get it over there. But this looks like it's not doing enough thing. Why this Vitess is working so effectively? And for that, we need to understand what exactly VT tablet is doing differently than normal MySQL instance. Think about this. So the major chunk of consumption of memory is the MySQL connection. So whenever there is a connection that needs to be established, that requires 2 megabytes of memory per MySQL connection. Vitess or VT tablet internally makes a connection pool where you don't need to create connection at every single instance. And that is when it serves a huge amount of efficiency over the normal MySQL clusters. Query rewriting. In certain cases, there are certain bad queries, like the very heavy queries without any limits would take down or take a huge toll on the database clusters, right? That is where we need to have proper structures in place so that the query rewritten and it doesn't affect any of the cluster's performance at all. The third and the most important thing is the query deduplications. In many cases, different people write different kind of queries, and which eventually serves as the same purpose. So the Vitess or the VT tablet makes sure that it dedupes the queries, stores it in cache, gives out the values if that's already in cache, and make sure that the duplicated queries doesn't reach the MySQL server at all. So this eventually, and the presence of many more components, make the Vitess such a huge success in the field of scaling MySQL instances. Okay, now that we have talked about the Vitess components, let's see how Twitter have integrated this Vitess in their architecture. Okay, so this on the left to this line is the architecture for the app, and on the right is the Vitess architecture that is inscribed into the read architecture that they have. So these are the app servers that they have, which is making a kind of read request to the user database. And there's this big data machine that kind of needs some kind of analysis to perform on the user's database. This VT-Gate, which I told you, was serving as a gateway for this request to reach the particular VT tablet, right? That means the VT-Gate, with the help of this topology service, knows that, okay, we need to reach to this shard 1 because we know that this information might be available in the shard 1, and it fires this request to the corresponding VT tablet in this case. This is replicated, this is master, this is replicas, and this is the read-only replicas. In case of any failures, this would get upgraded itself to the master and stuff like that. So all of the requests reaches VT-Gate here, and with the required configurations that is set up in Chubby or Zookeeper, which is internally the topology service, it reaches the corresponding VT tablet. And this topology service helps in making this resilient in case of any failures and stuff like that. And this VT tablet is connected to the MySQL daemon, which eventually performs the queries on this database. And while it returns back, VT-Gate makes sure to consolidate all of this information and sends it back to the app server that requested. And this is how the Twitter is managing hyperscale or million order query per second on this user's database. That's all for today, guys. I hope you liked the video. If you liked the video, do give a thumbs up to this video and subscribe to the channel for more such insightful videos in the future. If you have any comments or questions, please let me know in the comment section. I will attach all of the documents from the official Twitter's website and the documents that I have gone through before producing this article in the description below. And yeah, that's all from my side, guys. Thank you and have a nice day. See you in the next one.